Today is November the 15th, 2017. I'm going to attempt a video here to show how to measure high inductance coils like transformers. I've got a lot of audio transformers. Here's a nice one from Chicago Standard. Here's the James. Here's another one. This is I don't know if it's a Triad or a Thordarson. Here's another one. I'm not going to measure all of them. Here's a little push-pull 6V6 one, or 6BQ5 one, excuse me. Came out. That's a nice little transformer actually for that size. Here's some Triad 15 Henry, 120 milliamp, 185 ohm stuff. Here's some standards, 17.5 Henrys, 1 Henry. Here's a 50 Henry, 15 milliamp. But what I'm going to try to show you, and I say try because I'll warn you that these measurements can be pretty frustrating. It's very easy to measure and get consistent results from little chokes like this that don't have a whole lot of DC resistance in them. But once you get into the transformers, especially the audio transformers that are 20 to 40 and maybe even 50 and 60 Henrys, you end up in a different world. And these big iron cores just don't behave, even though they may not be a whole lot larger than, again, this example right here, 17.5 Henrys. They behave very different, and they become extremely tedious sometimes to measure. Well, let me show you what I've built here. Well, let me show you the schematic first. Here it is. It's actually quite simple in its schematic. It's got a voltage source right here. This is a 50 millivolt RMS. In LTSpice we put in peak voltage, and it's at 70 hertz. You might wonder why not 60. Well, every time I try 60 hertz, I just end up with a lot of interference. I suppose it's just the 60 hertz, you know, floating around in the room here. But anyway, this is a standard oscillator. It's actually this oscillator right here. It's just Tektronix SG505, and it plugs into my distribution box so I can watch it on whatever I want to, its frequency, its voltage, etc. Here's its output voltage right now. That's what I got it set for. That's 50.9. I'm not trying to make it exactly 0.9. I'm trying to set it at 50 millivolts. Let me turn it down here. You know, just close as I can to 50 millivolts. Not that 50 millivolts is any sacred number, but that's just what I've chosen. You want the voltage as low as you can get it and still be able to read it reliably on all of your meters. So there it is, 50 millivolts RMS is 70.71 millivolts peak, and that's what LTSpice wants to model it. Now, here's the inductor. This is L, and then I've got R series, and R fine. Now, this is just all one R as far as balancing it goes, but depending on the inductance, this resistor R only, in my box over here, I'll show you in a second, only goes to about 11K. So, and this one is 2K, the fine, and sometimes I have to add another one in series if I'm going up above about 12 or 13K. And this example right here is a 39 Henry inductor I have in it. Okay, so here's what I have over here. Here's the R, and here's the R fine, and here's the R series. I can unplug this if I don't need an R series, and then I just put the shunt across it like that. That's one way to do it. Or I can put a fixed resistor, you know, under the terminals like that if I just want to add 10K. Then I have a fancy little vernier pot here I was using, so you can dial it in exact. Well, here's where you put the oscillator in. I've got it measured as 50 millivolts. I had 30 hertz at one time, but I'm finding out that 70 hertz actually works best. Here's my unknown L. This is just in series with this, so I can put a current meter in there if I want to, or a capacitor. I've tried a lot of different variations, and this is where I read the half voltage. Actually, this is reading across these R's right here because they're all in series. Let me show you what it looks like underneath. I built it out of spare parts from a parted out General Radio device. This is an 11K pot. This is, I think, a 2K pot. This is my R and this is my R fine. And then see, it goes over here to this one where I can add some R series if necessary. Really beautiful potentiometers, aren't they? Really nice. Okay, so here's what we do. We set this thing up. I've actually got it hooked up to nothing right now, but I'll hook it up to something. Again, here's our voltage. So our voltage is coming in right over here. Right here. So what we have to do is, let's power up our meter, and we'll set it to millivolts so we can measure things very accurately. Range. There it is in the millivolt range. Of course, we're not doing anything right now. We don't have anything hooked across it. Let's hook this 50 Henry choke across it. Hope I can do this with one hand. I think I can. If we hook this guy across it, I'll show you some interesting things about it. Okay, I believe we've got it hooked up. I know it's a little crowded in here, and it isn't the clearest in the world, but see, this wire does go right around to here. This is just for another measurement. I don't actually need that in there right now. We can pull that off so it's less confusing parts. Okay, now what we want to do is set this to half, exactly half. And this is measuring in millivolts. Right now it's measuring 21.7. We want to set it to half of that right there. So that'd be like 25.2. I mean, we can get it down to exactly what we want. So I'll start out by turning the biggest pot right here, and we'll get it as close as we can. 25.2. We could probably set it right there just like that. Well, there's one. I can use this little vernier pot right here, or I can use this one, either one, because like I say, it's all just one series resistor. But I'll start cranking this one up to get to 25. Well, I'm cranking it down, aren't I? 25.2. We'll let it settle in just for a second. And it looks like it's pretty steady, and it's half of the one up there. The one that we just looked at was 50.4. Okay? Now that we've got the R balanced, what we have to do is take off the drive voltage, leave everything hooked up, except move, well, let's see, I've been doing it this way. Unplugging this one and plugging this one in so we can read the R value. This is where R is. This is across R. So now we're going to read R. And there it is, 12,578 ohms. 12.578K. 12,578. Okay, 12,578. We go down in here to our Excel program, 12,578. And right there we type in 12,578 and hit enter. Here is our frequency. I got it set at 70.07. There it is up there, 70.0708. I don't think the 07 and 08 makes much difference. But there's our R, and there's what it says our inductor is, 49.48 Henrys. That's pretty darn close, isn't it? Pretty close. Now here's an interesting thing. If you take this frequency right here and you determine X sub L, 2 pi FL, 2 pi F right here times this, the number that you get will not be this number. The number that you get by getting its inductive reactance and then multiplying it by the square root of 3 will give you this number right here. So this method actually works pretty good. This is for a 50 Henry choke, so it's telling us that we can reasonably accurately, it seems, measure these things. Okay, let's just do one or two more examples. Let's take this James transformer. This is actually what sparked this whole thing, and let's measure it. I'm measuring it plate to plate. The smaller inductances are easier to measure than the high ones. Okay, see, now we're down at 12.4. Okay, whoops, no, I'm sorry. Whoops. we got to plug this back in, and we've got to unplug this one and plug this back in. Okay, now maybe we can get somewhere. Okay, it's higher now, so that's telling us basically from what we just measured that the inductance is going to be lower. So I'm going to start turning one of these 3 pots, whichever one it takes to balance this thing down to half again, which is still 25.2. You can see it going down and down. Okay, I'm going back up with it now. I'm just moving this pot right here, and 25.2. I've got to turn this one down a little bit. 25.2. Okay, I've got to make some adjustments here. Stand by. Be right back. Okay, I had a little interruption there, but let's crank it on down to we get the right number. Actually, I'm turning this little pot right here. Isn't that a neat little pot? Well, see, now I've gone too low, so we want to come back up to about 25.2. Sorry for the glare. Here it is. Let's let it settle in. Get it as accurate as we can. Okay, so our 25.2 now is half of the 50.4 millivolts. See, that's 0.0503 or 0.0504, which one is fluctuating between. So that's 50.4 millivolts. So this would be half. You want this down at 2, I believe. Darn. Don't mean to make it so tedious here, but I'm cranking on it. Okay, that's pretty darn close. So let's stop there. Now we got to do this same procedure again. Remember, we're measuring the inductance from plate to plate. These measurements can be a little tedious and difficult. We're going to measure but we got to take our driving voltage off. And there's its number. 6,977 ohms. 69, 76, 77, 69, 76. 69, 76. So we put that in here. 69, 76. And hit enter. Everything else is the same. Our frequency is the same. It says it's 27.44 henries. That's probably about right. I actually don't know exactly what it is, but that's a pretty reasonable number. It's probably 20 to 25, maybe 27. I tend to believe it. And here's another good point. If you're going to, the purpose of learning how to do this was, one, to share it on YouTube so that there is a reasonable way to measure the inductance of these coils, transformers, whatever. And another is, the primary reason I started all this was to be able to measure the transformers and be able to model them in LTSpice. So this will work very well in your LTSpice program. Now, we can go on, and if we get these like this 17.5 Henry, well, let's do one more. Let's do the standard so that you can see that this procedure actually works fairly well. If I can do all this with one hand. I got that hooked up. Yeah, got to have good connections. Good connections are absolutely necessary. Okay, now we've got to put our meter back over here, and we got to put our driving source in here, and we'll repeat one more time here. Okay, see, it's 30. Okay, we got to get back down to 25.2. See if we can get there without having to. I may have to pull this guy out right here and put the shunt in. We'll see. 25.2. No, looks like I'm going to be able to get there. There it is right there. 25.2. Okay, so it's pretty well balanced. So we gotta pull this guy back out, put our ohm meter across it once more. We just keep repeating this process for each one. Now it says our number is 5,114 ohms, or 13 ohms, or 14 ohms. 5113. Let's put in 5113. That's the only number we got to change in here. 5113. It says it's 20 henries. It's a little bit different, isn't it? .5113. Is that right? That's what we got. 5113. Well, it doesn't measure it exactly right, but this is the challenge with this. So with all this said, you may say, well, this is pretty worthless because it doesn't give me the exact number. Well, I hate to tell you, but you're probably not going to be able to get the exact number. A lot of things come into play here. So this is one method. There's another method that I don't want to go over right now because it'll just probably become really tedious. Yeah, it's all right. I expected it to be a little bit closer than that. Let's recheck it. And I guarantee you will get different values at different frequencies. Now we know that inductance is not frequency dependent. Inductive reactance certainly is, but the frequency that you measure the inductance at does matter. 25.2, so it balanced out right. I don't see a problem with the measurement that we made. It didn't give us 17.5. The GR measures this one a lot of times at about 18 to 18.5. Let's do one more. Let's do this 15 Henry one right here. Let's see what it says this guy is right here. This one actually measures on the GR at 14 very consistently. But measuring these chokes and measuring those audio output transformers is, again, a different world. This guy right here and this guy right here are not the same. Okay, let's balance it again. I think I may have to pull this out. I think I'm going to go ahead and pull that out and then just put the shunt across it. So we don't need that resistor in there because we're going down in value. Now then I can crank this one back up. See how I crank it up to increase it. So it gets kind of tedious here. 20, what do we want now? 25.2. I'm turning it very, very slowly here. Here I think you can see my fingers. 25.12. Okay. That's close enough. And then I can trim it with this one over here. This one and this one. Well, with this thing plugged in, it makes it a fine. There's 25.2. Okay. Let's do our procedure again. Let's plug our ohm meter in and remove the drive and see what the number is. 3,674.2 ohms. Let's call it 3674. 3674. Let's put 3674 in there. 3674. Enter. 14.45. 14.454. 14.5 henries. Right there. And it says it's 15. So there again, we're pretty close. Close is better than just blindly guessing. I guess that's kind of what it's worth. When you measure with this nice device right here, on these small cores like this, you'll get pretty much the right answer, and this one will be spot on one. But if you measure them at different frequencies, you can get different numbers. Sometimes you will, sometimes you won't. The smaller ones like this, you tend to get the same numbers even at different frequencies. These right here, the more complicated, the higher the inductance, the stranger it gets. Here's got to do one more. This is actually working pretty well. The connections that you make are so critical that everything be such good connections. So let's measure across this guy. This is a very high inductance choke, or not choke, but output transformer. You got to make darn sure that none of your wires are touching each other. There's the blue and the blue-white. So that's across the whole thing, across plate to plate. See, we can see that this one is way down. So I know we're going to have to add a resistor to it, and I hope this one right here is big enough. So we're going to have to go way up here. Okay, yeah, it's going to be good. 25 point. Okay, and then I'll trim it out with this one, because this one's is really precision. 25.2. There you go. Right on. One more time. And let's see what this one comes out to be. This one's usually pretty high. Okay, 10,198 ohms. 10,200 ohms. 10,200 ohms. 10,200 right there in that cell. Everything else is staying the same. It says it's 40 henries. I totally believe that. I think that's actually pretty darn good. I think that's really pretty good. I misspelled radians up there, didn't I? Fradians. Anyway, there you go. Hope this is worth something. You can find the write-up on this method on the internet. You got to be careful. I'm going to tell you once more, I can't guarantee you're going to get the results that I get. I can't guarantee you're going to get the results that you want. I can't guarantee you're going to get the correct results. But like I say, it's better than just blindly guessing. Well, what's the inductance of this guy? Well, I don't know. Somewhere between a Henry and 100 Henries? Well, yeah, probably. But it'll put you in the ballpark, and it'll give you close enough numbers that if you want to use them in your LTSpice models, I think you'll be just fine. My many thanks to Bob up in Iowa for helping me out. Bob knows a lot more about transformers and LTSpice than I do, and he kept me straight. We've been working on this together for at least the last 3 weeks, writing each other pretty much every night. And he's been modeling them, and I've been in here hacking away and drilling all these holes and making this thing. So there you go. I hope this helps. It's not the perfect answer, but it's better than no answer at all. That's the way I look at it. Thanks for watching.